Okay, so let's jump right in. Here's something maybe surprising. Did you know over half, over half the entire world's oil reserves, they're actually sitting in fractured carbonate reservoirs?
That's right. It's a huge amount, and it hides, well, just an incredible amount of complexity under the surface.
It really is. I mean, it's the ultimate puzzle, right? When you're trying to predict how fluids flow, especially in things like, tight formations, deep shales.
Yeah, exactly. The accuracy there doesn't just depend on the rock itself. It's almost entirely down to how you actually describe the fractures within that rock.
And these fractures, they're just incredibly dominant, aren't they? They might be super thin,
Mm.
physically tiny in volume.
But they're huge compared to the little pores in the rock matrix.
Uh-huh.
They can stretch across entire fields.
Right, so even if they make up like a tiny fraction of the actual rock volume.
They're the main highways, the main plumbing system for fluid movement.
Exactly. So how do engineers deal with this? I know there are these things called DFM models.
Yep, discrete fracture matrix models, or DFM, that's the approach where we try to explicitly model those really big, important fractures. We treat them as lower dimensional sheets, like 2D surfaces embedded inside the 3D rock volume.
Okay, like flat sheets representing the fractures.
Precisely, yeah. Flat sheets or polygons within the 3D space. It's theoretically a great way to capture that really important exchange of fluid between the slow-moving porous rock, the matrix, and the fast flow happening in the fracture itself.
But only does a but, isn't there?
There is. It creates a computational nightmare.
Meshing. I
Yeah.
was waiting for that.
Meshing, exactly. Making the computational grid, that 3D grid you need for simulations, making it stable and usable when you have these complex fracture geometries. That's often the single biggest hurdle.
Right. So that brings us to our mission for this deep dive. We're going to unpack a new open source method called DFNMesh. It's specifically designed to tackle this mesh stability problem, especially for people using multiscale finite element methods, right?
That's the key context, yes. Multiscale finite element methods, or MSFEMs. With MSFEM, you absolutely rely on having a good, robust coarse grid to start with.
Why is that initial coarse grid so critical?
Because the whole point of MSFM is to calculate flow properties on those large coarse blocks based on what's happening at the finer scale within them.
Yeah.
If that underlying coarse grid is unstable or has badly shaped elements or, gaps.
The whole simulation just falls apart.
Exactly. The whole multi-scale calculation collapses.
Okay, I get that. And it makes sense why DFM has this reputation for being, well, a pre-processing headache. Because those 2D fracture sheets, when they start intersecting inside your 3D volume,
They become geometric constraints for the meshing software. And every fracture you add, especially if they intersect, just ramps up the complexity almost exponentially.
and standard meshing tools are the general purpose ones,
Yeah.
they just can't cope.
Often, no. Their algorithms are usually built for optimizing element quality in relatively simple geometries. When you throw in these highly constrained intersecting internal surfaces, they can get pushed past their limits. You end up with, well, what we call pathological
It's
geometry.
infamous sliver
The
element.
sliver elements, yeah. Elements that are squashed almost flat, near zero volume. Or triangles that are incredibly stretched out and distorted. Or sometimes the mesher just gives up entirely, crashes, because the geometry is just too challenging.
So historically, what did people do?
Well, specialized tools often had to use something called feature rejection,
Which means
literally deleting or modifying small geometric features that cause problems. Like if two fractures almost intersect or intersect at a super sharp angle, the tool might just snap them together or slightly move them.
But that means you're changing the input data.
Right.
You're distorting the geology you were trying to model in the first place.
Precisely. That's the trade-off. You sacrifice some geometric fidelity to get a mesh that actually works.
Or I guess you could use alternative modeling approaches. You mentioned EDFM before.
Right. Embedded discrete fracture models. EDFM is another popular approach. It simplifies the meshing problem significantly
Wow.
by using non-conforming grids. This means the grid cells for the rock matrix and the grid cells for the fractures don't have to line up perfectly at their boundaries. It makes meshing much easier.
But you lose that perfect connection, that conformity between the fracture and the matrix.
You do. And that's where DFM, and especially DFNMesh, tries to be different. They aim for full grid conformity, making sure everything lines up neatly. It's generally better for accurately modeling the flow exchange.
But much harder to mesh.
Much harder. And this is why DFNMesh's core idea is, well, quite clever.
Okay, what makes it so unique then?
The absolute primary constraint for DFNMesh is the user's predefined coarse mesh, the starting grid you give it. DFNMesh has to preserve it.
Preserve it how? It has to cut fractures into it, right?
Yes, but it does it through refinement only. It never moves the original coarse grid nodes. It essentially flips the problem on its head. Instead of trying to generate a complex mesh all at once, fitting fractures in as you go.
Which often fail.
Right. Instead, DFNMesh takes your existing, stable, maybe simple coarse grid and turns the problem into a sequential refinement task.
Ah, okay. So you give it a solid foundation, the coarse mesh, and say, right now, carefully cut these fractures into this existing structure, one after the other.
Exactly that. It's about building stability from the known coarse scale downwards, guaranteeing that the large-scale connections defined by your initial grid are always respected.
That sounds much more robust.
Yeah.
Let's get into the nuts and bolts of that refinement then, because you mentioned trade-offs earlier, and I imagine this is where they come in. You said there are, like, 4 key rules or premises?
Yeah. Yes. 4 foundational rules that guide the whole process, all aimed at robustness. First, coarse mesh conservation. Like we said, discretization only happens by refining existing elements. Critically, the coordinates of the original coarse mesh nodes are never changed. Never.
So your initial large-scale domain stays exactly as you defined it. Stability first. Got it.
Second, sequential insertion. Fractures are inserted one by one. This sounds simple, but it has a really significant implication.
Which is?
The final mesh geometry, the fine details, can actually be different depending on the order in which you insert the fractures.
Hang on. If the final grid depends on the order I put the fractures in, doesn't that introduce a kind of, I don't know, user bias?
Yeah.
Subjectivity.
It absolutely does, and that's a conscious trade-off that developers made in favor of guaranteed stability and mesh generation success.
So you have to decide which fractures are more important.
In a way, yes. It forces the geologist or engineer to think about the fracture network's hierarchy. If you have one massive fault that you know dominates the flow,
You put that one in first.
you make sure that one gets represented as accurately as possible by the refinement process, even if enforcing its geometry slightly distorts how a later, perhaps less significant, fracture gets meshed when it intersects nearby. It makes modeling less of a black box and more of a process requiring judgment.
That's really interesting. A trade-off for sure, but I can see the logic. Okay, what are the other 2 premises?
Third, local convexity. Any geometric shapes involved in a cutting or refinement operation are either already convex or are forced to become convex. This drastically simplifies the maths of splitting elements.
Makes sense. And the 4th?
Fourth, conformity. This is crucial. If a fracture cuts through the side, like an edge or a face of a coarse element, that intersection line must be extended across all the other coarse elements that share that same edge or face.
Ah, so that's how it guarantees that the final refined elements meet up perfectly, without gaps or overlaps across the original coarse boundary.
Exactly. It ensures the final 3D mesh elements will interface cleanly.
Okay, so with those rules in place, how does it actually cut a fracture in, step by step?
Well, it starts by finding intersections between the fracture polygon and the edges of the coarse elements it passes through. A fracture plane divides space, right? Positive side, negative side. If an edge has one endpoint on the positive side and the other on the negative,
It must cross the fracture plane somewhere.
right, the code calculates that intersection point. Then it checks if that point actually lies within the bounds of the specific fracture polygon you defined. And it includes careful checks and tiny corrections to handle potential floating point precision issues, the quirks of 64-bit numbers.
So it finds all the edge intersections first, then what?
Then it looks at the faces of the elements. Faces that contain intersected edges must also be intersected. These faces are then refined, split into smaller polygons, using a set of predefined split patterns. Because of the convexity rule, there's a limited, manageable number of ways a face can be split by the fracture intersection lines.
Okay, this sounds very systematic. But where does the feature rejection or distortion come in? You mentioned that earlier.
Yes. That comes in via the snap operations. This is the critical control mechanism. It's where the user directly balances the geometric fidelity, how true the mesh is to the input fracture data, against the quality of the resulting mesh elements.
So this is DFNMesh's version of that feature rejection we talked about, but it's more controlled.
Exactly. It's the necessary compromise, the Faustian bargain, if you like. Instead of just letting a tiny intersection feature, one that's maybe numerically problematic, create a horrible sliver element that ruins your simulation.
It forces that problematic point to merge with something more stable.
Precisely. It snaps the calculated intersection point onto an existing, nearby, stable grid point, usually a node or a corner of the element.
And what triggers this snapping? is it automatic?
It's triggered by tolerances that you, the user, define. There are two main ones. First is a distance tolerance. They call it epsilon. Epsilon. If the calculated intersection point on an edge is extremely closer than your epsilon value to one of the existing nodes at the ends of that edge.
You just snaps it to that node like,
Yeah.
hey, close enough.
Pretty much. The logic is it's so close, the difference is likely noise or will create a tiny unstable element, so let's just consider it the same point as the existing node.
Okay, makes sense. And the second trigger, you mentioned angles.
Yes, an angle tolerance, epsilon alpha. If the process of refining a face or edge creates new internal angles that are too sharp, below your tolerance.
Which would lead to poor quality, maybe sliver-like elements.
Exactly. If that happens, the system again avoids creating that sharp angle by snapping the problematic intersection point to an existing corner of the element instead.
So these snap operations definitely improve the mesh quality, preventing those bad elements.
They do, significantly.
But they do it by actively distorting the mesh, moving the fracture representation away from its original input geometry.
That is the explicit trade-off. You are consciously allowing, even controlling distortion to guarantee a stable, usable mesh.
Right. But the payoff, especially for those multiscale methods, is the final output grid. After all this sequential insertion, refinement, and controlled snapping, what does the final mesh look like?
The key result is that you get a conformal mesh, everything lines up, that is completely free of non-manifold features.
Non-manifold. What does that mean in simple terms?
It basically means the grid is geometrically tidy. You don't have impossible situations like an edge belonging to 3 different faces instead of just 2, or a vertex where surfaces improperly connect. Every connection is clean and topologically sound, like a well-behaved 3D grid should be.
And having that clean, non-manifold conformal structure makes the next step easier.
Much easier. It makes the final step of filling the volumes with 3D elements like tetrahedra, which DFNMesh often uses Grimsh for, far less demanding and much more likely to succeed without errors.
That guarantee of a clean structure sounds incredibly valuable. Okay, let's see how this actually performed. They tested these meshes in flow simulations using the mixed finite element method, MFM. Why MFM specifically?
MFM is really valued in fluid dynamics because it gives you what are called locally conservative approximations of the velocity field.
Meaning?
In simple terms, it mathematically guarantees that for any block or element in your mesh, the amount of fluid calculated as flowing in must exactly equal the amount calculated as flowing out. Mass conservation is strictly enforced at the element level.
Which is obviously critical for flow modeling.
Absolutely. It's often considered a gold standard for that reason.
Okay, so benchmark 1. They designed this one specifically to test how DFNMesh handles those tricky, small geometric features, fractures almost touching or intersecting at very sharp angles, the things that usually cause meshes to fail.
Right. And they ran 4 cases, labeled A through D. The only difference between them was the snapping tolerance they used. Case A had very small tolerances, very little snapping.
So most faithful to the original geometry.
Yes, but likely creating the most complex mesh with potentially lower quality elements near those tricky features. Case D, at the other extreme, used large tolerances, allowing for much more aggressive snapping.
More distortion, but potentially a much cleaner, higher quality mesh.
Exactly. And the results showed this trade-off visually. Case D, the one with high snapping, had a significantly better gamma quality metric. That's a standard measure where 1 is a perfect element, like a cube or equilateral tetrahedron, and values closer to 0 are worse. Case D's mesh elements were, on average, much closer to ideal shapes.
But the geometry was noticeably different from Case A.
Oh, definitely. In Case D, the aggressive snapping had clearly coalesced features. You could see gaps between fractures that existed in Case A were closed in Case D. Fractures that were originally distinct got merged together.
And did this distortion affect the simulation results? Could you see it?
Yes, you could. They pointed out one specific example where a diagonal fracture got snapped onto a nearby horizontal one in Case D. In the flow results, you could see an unnaturally abrupt change in pressure right at that junction, where the flow path was forced to change sharply due to the snapping.
Wow. So that the meshing process itself introduced a visible artifact in the flow pattern. That sounds bad.
It sounds bad locally, but here's the crucial finding. Did it ruin the overall prediction?
Did it?
No. That was the key takeaway. Despite those visible local distortions caused by snapping, All four meshes from the most geometrically faithful case A to the most distorted case D produced overall hydraulic head results, which is like the pressure potential driving flow, that were consistent with each other and, importantly, consistent with results from other established benchmark methods reported in scientific literature.
Okay, that's the punchline. Even with noticeable local distortion, the stability gain meant the overall macro-scale flow behavior was still captured reliably.
Exactly. It strongly suggests that for these large-scale, multi-scale simulations, guaranteeing mesh stability and usability, even at the cost of some local geometric detail, is often more valuable than chasing perfect microscopic fidelity that might lead to a mesh that doesn't even run.
That's a really powerful result. What about complexity? Did they test it with, like, a lot of fractures?
They did. Benchmark 2 was designed for robustness. They threw 52 fractures into the domain, creating a much more complex network with many intersections.
Did DFNMesh handle it?
Yes. Again, they ran cases with varying snapping tolerances. And even with the significant number of fractures and the inevitable distortion needed to make the mesh work, especially with tighter tolerances, the generated meshes were stable, and the flow simulation results were consistent and fell well within the range of results expected from the benchmark definition. It proved DFNMesh could handle geologically relevant complexity without failing.
That's impressive robustness. Okay, last piece. Performance. How fast is it? Because stability is great, but if it takes forever.
Right, they looked at scaling. In a test case with just a single fracture, but run across increasingly large coarse meshes up to 1 million coarse elements.
How did the time scale?
It scaled linearly with the number of coarse elements, which is very good. It means the refinement approach itself is efficient. Doubling the number of coarse elements roughly doubles the time. It doesn't explode.
That's the ideal scenario, really. But what about the other end? Lots of fractures. That sequential insertion, you said it depends on the order. What's the worst case?
They tested that too. A limiting case. They put multiple fractures, all essentially coincident, all passing through the same single coarse element volume. This forces the algorithm to do the maximum amount of refinement and intersection checking in one tiny region.
The absolute worst case for intersections.
Pretty much. And in that scenario, the computation time grew in cubic order relative to the number of fractures packed into that one volume.
Ouch. Cubic growth. N cubed. That gets slow fast.
It does. It's the reality check. It shows that while the algorithm is generally efficient and robust, there's no magic bullet. When the underlying geometric complexity becomes pathologically concentrated, the computational cost will still rise significantly. Geometry ultimately dictates the difficulty.
Makes sense. You can't completely escape the physics or the geometry of the problem?
Nope.
Okay, so let's try and wrap this up. DFNMesh emerges as this really robust meshing approach. It uses that sequential refinement idea, starting from a user-defined coarse grid, guarantees a final mesh that's conformal, no weird non-manifold stuff.
Right, guaranteeing usability.
Its main value seems to be giving control back to the user over that crucial coarse discretization, which is vital for multiscale methods like MSFM. And it achieves this by being willing to trade some geometric perfection for guaranteed stability using those controlled snap operations.
That sums it up well. It prioritizes a successful mesh generation and simulation run over absolute fidelity to potentially problematic input geometry.
And they're not stopping there. What's next for DFNMesh?
They mention a couple of future directions. One is looking at pre-computing which coarse elements are intersected by which fractures. This could potentially automate some of the pre-refinement steps users might currently do manually, maybe allowing for even coarser starting grids.
That would definitely streamline the workflow.
Yeah.
Anything else?
They also talked about tackling that cubic scaling in the worst case by exploring parallel programming, specifically for the intersection searching and the surface meshing parts. Parallelism could definitely help speed things up, especially for those really complex fracture-dense models.
Makes sense. Use more computing power to brute force the complex bits faster.
Essentially, yes.
So this whole deep dive leaves us with a really interesting final thought, doesn't it? The DFNMesh authors made a very conscious choice. They gave up the potential for the most geometrically perfect mesh, according to some mathematical optimum,
In favor of giving the user control over the coarse grid and guaranteeing stability.
which, as the benchmarks showed, seems essential for actually getting reliable answers out of these complex multiscale simulations. It raises that bigger question for anyone modeling these massive, inherently messy geological systems. Where's the point of diminishing returns on geometric accuracy?
Exactly. At what point does the need for computational stability and the ability for the expert user to impose their judgment on the model setup via that coarse grid become fundamentally more valuable than chasing ever finer microscopic geometric fidelity to input data that is itself always uncertain and imperfect?
A question of balancing theoretical perfection with practical simulation. Food for thought indeed.